In the previous video, we have seen that methods of preparation of alkyl halides from alcohols by using the reagents like PCl3, PCl5, SOCl2, HCl, etc. These reagents are able to break the bond between alkyl group and OH, and in the position of OH, halogen atom substituted. Can we apply same method to convert phenol to haloarenes by using same reagents? The answer is big no. We cannot use all these reagents to convert phenol into haloarene, even though phenol is also having one hydroxyl group attached to the carbon, as in case of alcohols. We cannot use all these reagents to substitute the OH group by halogen atom. The main reason is, in case of alcohols, the hydroxyl group is attached to sp3 hybridized carbon atom, but in case of phenols, the hydroxyl group is attached to sp2 hybridized carbon atom. Here, the hydroxyl group in case of phenol is attached to sp2 hybridized carbon atom. How to decide whether a carbon atom is sp3 hybridized or sp2 hybridized or sp hybridized? A simple logic I will give you. If the carbon is surrounded by single bond, it is sp3 hybridized. If a carbon has a double bond, it is sp2 hybridized. If the carbon has a triple bond, then we say that it is sp hybridized. In case of phenol, the OH group is attached to sp2 hybridized carbon atom, and sp2 hybridized carbon atoms are more electronegative, because we know the electronegativity order is sp hybridized carbon is more electronegative than sp2 hybrid than sp3 hybrid carbon, because the electronegativity of hybrid carbon depends upon the percentage of S character. If we find the percentage of S character in sp hybridization, that is, we have to divide 100 by 2, that we get 50% is the S character. Here we have to divide 100 by 3, because here in sp2 hybridization 3 atomic orbitals they have undergone mixing, therefore we have to divide 100 by 3, therefore we get 33%. This is the S character in sp2 hybridization. And in case of sp3 hybridization, we have to divide 100 by 4, because here there are 4 atomic orbital, 1s and 3p have undergone the process of hybridization, therefore we have to divide 100 by 4, so we get 25%. This is the S character in sp3 hybridization. If we compare the S character of sp2, that is 33%, and sp3 is 25%. As the S character in sp2 hybridization is maximum, it pulls the electrons of oxygen and it creates a partial double bond character between carbon and OH group. Therefore, the bond length, as the bond has partial double bond character, bond length between carbon and OH, it reduces to 1.38 picometer approximately. It becomes 1.38 picometer. The bond length in alcohol, that is carbon and OH, is 1.40 picometer. So the bond length in case of phenol is shorter than that of the alcohol. Therefore, it requires more energy to break the carbon and OH bond. So these reagents, they are unable to break the carbon and OH bond in case of phenol. So by using these reagents, we cannot produce the haloarenes. And one more very important reason is these lone pair of oxygen, they are involved in the resonance of the benzene ring. Therefore, the phenol is resonance stable. Therefore, it is difficult to break the carbon and OH bond. So we cannot use these reagents to convert phenol into aryl halides, that is haloarenes. Then the question arises, is it not possible to prepare the haloarenes? The answer is yes, we can prepare the haloarenes, but there are some different methods. Here we will see one by one. Preparation of haloarenes. The first method is direct halogenation. It is an electrophilic substitution reaction. When chlorine and bromine, they react with aromatic hydrocarbons in presence of Lewis acids such as iron FeCl3, LCl3, BF3 in dark, and they produce chlorobenzene and bromobenzene respectively. Here Lewis acids, they act like catalyst and they are halogen carriers. How they behave like halogen carriers we are going to see in the mechanism. I will explain you the mechanism of this reaction and how this Lewis acid act like catalyst and it acts like halogen carrier, and I will also give the answer for why this reaction is carried out in dark, why not in light. I will give you the reason for this also. Here we see the mechanism. Chlorine reacts with benzene in presence of Lewis acid AlCl3. It gives chlorobenzene. Mechanism of this reaction. Mechanism. First step. In the first step, chlorine undergoes heterolytic fission. Heterolytic fission means what? Both the electrons are taken by one chlorine atom. Therefore, it becomes minus and this chlorine becomes plus. Now, this Cl minus combines with the Lewis acid and it gives AlCl4 minus, AlCl4 minus plus this Cl plus. This is electrophile. In the first step, electrophile is generated. Now, step 2. In step 2, benzene, it undergoes the heterolytic fission. Here, the double bond electrons are given to one carbon atom. Therefore, this carbon atom becomes negative and this carbon atom becomes positive. And this electrophile Cl plus, it attacks to this carbon atom which is having a negative charge. So, we get the electrophilic attack. This is Cl. At the same time, here this carbon is also bonded with a hydrogen, right? Each carbon is bonded with one hydrogen in benzene. And now this carbon is positive. Therefore, it withdraws the electron from hydrogen and it restores the double bond. So, finally we get chlorobenzene plus H plus, that is proton. This proton will again react with AlCl4 and it forms HCl. Now, I will give you the reason why the reaction should be carried out in dark. This reaction must be carried out in dark because if we carry out in the light, the electrophiles are not generated. Electrophiles are not generated. Why? Because chlorine may undergo symmetrical breaking and it can produce the free radical. If free radical is formed, this reaction will not take place. Therefore, in order to avoid the formation of free radical, the reaction is carried out in dark. Now, I will explain you once again the mechanism. The direct chlorination of benzene or bromination of benzene in presence of any Lewis acid, it takes place in two steps. In first step, the electrophile is generated. Here, the chlorine or maybe bromine, it undergoes the unsymmetrical breaking and we get the electrophile. In second step, the double bond breaks unsymmetrically and the carbon becomes negative. The electrophile attacks the negative carbon and we get an intermediate. Here the carbon is positive, so carbon cannot be positive for longer period, so it withdraws the electron from the hydrogen because hydrogen is better leaving group, so the bonded electrons from hydrogen are taken by this carbon and double bond is restored, so we get chlorobenzene. Same mechanism we can apply for the bromobenzene also. Now let us see the preparation of chlorobenzene from toluene. Benzene having CH3 group is called as toluene. When toluene is reacted with chlorine in presence of Lewis acid like FeCl3 in dark, we get two products. The reason for this is this methyl group is ortho and para directing. Methyl group, it increases the electron density at ortho position as well as at para position. So we get the ortho product, that is orthochlorotoluene, and we also get para product, that is parachlorotoluene. That means the electrophile generated, it will attack at ortho position and few electrophiles they go to para position, and here we get two products. Out of these two products, one is formed in larger quantity, that is called as major product. Para product is a major product, means it is formed in larger quantity, and the ortho product is minor product. This is formed in smaller quantity. The reason for this is the incoming electrophile, it has hindrance, it has the opposition by a bulky group like CH3. So the electrophile, it prefers to go to that position where there is less crowd, so it will come to para position. We can take one simple example. If we go to railway station, we are standing in a queue for the ticket. We prefer to stand in that queue where there is less crowd. Same thing here crowd is there, so less electrophiles they prefer to join this position and more electrophile they prefer to join the para position. Therefore approx 80% of para product is formed and 20%, approximately 20% minor product is formed. The name of this compound is orthochlorotoluene and the name is parachlorotoluene. Again I will explain you why the reaction is carried out in dark. The reason here is, if the reaction is carried out in light, there is possibility of chlorine to attack on methyl group instead of attacking on the benzene ring. So we do not get this product if the reaction is carried out in light. So in order to avoid the side chain reaction, the reaction is carried out in dark. Now let us see the mechanism of this reaction. In first step, chlorine undergoes heterolytic fission and it reacts with FeCl3 and it gives FeCl4 minus plus Cl plus. The electrophile is generated. In second step, the toluene the double bond breaks unsymmetrically and it gives here the negative charge. So this carbon becomes minus and this carbon becomes plus. Okay, and one hydrogen is also present here. Now the electrophile Cl plus will attack to this carbon atom. So we get this is CH3 and this carbon is positive, here hydrogen is there and here attack of electrophile has taken place. The carbon cannot be positive for longer time, so it withdraws the electron from the hydrogen, because hydrogen is a easy leaving group, and we get finally the ortho product, orthochlorotoluene plus H plus. This H plus will combine with this Cl and it gives HCl. Similarly, the reaction also take place at para position. If you see here, the double bond, it undergoes the unsymmetrical breaking. Here this carbon becomes negative and this carbon becomes positive, and this is the hydrogen atom of the benzene. So the electrophile attacks to the para position and we get here hydrogen, here Cl, and this carbon is, as it is positive, this carbon withdraws the electron and it restores the double bond. So we get the product like this, parachlorotoluene. Now let us see the reaction. If the reaction of toluene and chlorine is carried out in presence of sunlight, what happens? When toluene is reacted with chlorine in presence of sunlight, that is UV light, that, or you can also write H nu, we get a product CH2Cl. We get benzyl chloride. The reason is the reaction take place according to free radical mechanism. You have to remember that when any reaction, when halogenation reaction is carried out in presence of light or sunlight or UV or H nu, the reaction take place according to the free radical mechanism, and always free radical mechanism, it results into side chain product. Halogen will not attack to benzene ring, halogen will attack to the side chain, so we get side chain product. So we get here benzyl chloride. If we continue the chlorination reaction, one more hydrogen is replaced, so we get CH, and if we continue chlorination, finally the last hydrogen atom is replaced by chlorine and we get CCl3. Now one question, what is the product in this reaction? If you see here, we are carrying out the chlorination in presence of UV light. That means free radical reaction is going to take place. Free radical reactions, they give side chain products. Therefore, the question comes in our mind whether the chlorine free radical replaces this hydrogen or this hydrogen or this hydrogen. Here we have to take into consideration the stability of the free radical. If the free radical on this carbon atom is formed, that is the primary free radical. Here the free radical is formed on this carbon atom, that is secondary free radical. If here free radical on this carbon atom is formed, this is benzylic free radical. Why it is benzylic free radical? Because the free radical is formed on that carbon atom which is attached to the carbon atom having double bond. So benzylic free radicals are more stable than tertiary, than secondary free radical, than primary free radical. I will give you the stability of free radical order. Stability order for free radicals, so that it becomes very easy for you to decide which product is going to form. allylic free radicals are more stable. Allylic free radicals are more stable than benzylic, than tertiary, than secondary free radical, than primary free radical, than methyl free radical. So this is the stability of the free radical. If in this question the free radical, if it is formed here, it is primary free radical, which is less stable, and if the free radical is formed here, the chlorine can attack on this secondary free radical, but secondary free radical is less stable. And if the free radical is formed on this carbon atom, that is benzylic free radical, which is more stable than secondary and primary. So we are going to get a product like this. Chlorine will attack on this carbon atom and we get a product like this. I hope you have enjoyed this video, and in the next video we are going to learn few more methods of preparation of haloarenes, that is from diazonium chloride salts. Thank you for watching. I am thankful to YouTube and millions of YouTube viewers.